So now that we've covered Diels-Alder problems, we're going to discuss how do we move backwards? How do we take the product of a Diels-Alder reaction and determine the reactants that were used to make that product? So what I like to tell students is to identify the position of the pi bond. That's why I've highlighted in yellow. If you identify the position of the pi bond, then you can skip let me find my pen. Okay. So once you've identified the position of the pi bond, we're going to move to the carbon that is one single bond away. So actually you can label the carbon one single bond away. As one, and the C two single bonds away. Two. So if we do that for both of them, both the carbons that are one single bond away and both the carbons that are two single bonds away, what that gives us is the new bond that was created. So those are our new sigma bonds that were made, and I'll highlight those in green. So yellow is the new pi bond. And green are the new single bonds. Okay. Or new sigma bonds. And so in the original structure, there should be a bond between, there should not be bonds between 1 and 2. So if we first erase those sigma bonds, and then we will have our piece that is 4 carbons long and our cis-diene okay, and then we have to say that originally the pi bond was not at that position. Originally the pi bond was between these carbons. So we erase the pi bond for the dienophile and draw in the original positions for the pi bond. And that will give us our diene and our dienophile. So we note to delete this pi bond, add pi bonds on either side of the position that this pi bond is at. Then we delete the sigma bond here and here, and we add a pi bond for our dienophile carbons so that we get our final product. Okay. Another way to look at this is to identify the position of the pi bond, go 2 carbons away, and then break that bond on both sides. So we've drawn this red line across the 2 sigma bonds that are going to break, and we've highlighted these 2 ends of this hexagon because these were the original positions of pi bond, because this is the new position of the pi bond for the dienophile, and it has to be erased to make pi bonds on either side. And then this is the original position for the dienophile. So we add pi bonds on either side of the existing pi bond, delete the sigma bonds, and add a pi bond for our dienophile. Delete, add. So that our original molecule is this cyclopentadiene and this carboxylic acid. And this molecule, the cyclopentadiene, is equal to this molecule here. Okay. So that covers Diels-Alder reactions, and now we're going to move to more information about delocalization energy and a special type of delocalization energy in terms of aromaticity. Okay, so cyclohexene with its 1 pi bond takes negative 28.6 kilocalories per mole to in energy. And then so if the electrons were localized, then the total energy to remove all of the pi bonds for a triene, for a cyclic triene, should be negative 85.8. So this is the energy for this 1 pi bond, negative 28.6. If we multiply this number by 3 and have a cyclic structure with 3 pi bonds, if these electrons are localized, so if these electrons are also localized, the delta H should be negative 85.8. However, the actual delta H for this molecule is called, which is called benzene, to add 3 times H2 requires only negative 49.8. So the difference between the value of localized triene electrons and the delocalized electrons of benzene, the difference in those values is called the delocalization energy. So the delocalization energy for benzene is 36 kilocalories per mole. Okay. And this delocalization energy for molecules like benzene is attributed to their aromaticity, their delocalized electrons. And we have some characteristics for how to recognize when a cyclic molecule is aromatic. There are several rules that must be followed. And you need to know these rules and to be able to identify whether a molecule put in front of you is aromatic or non-aromatic or anti-aromatic. And we'll have to define what non-aromatic and anti-aromatic mean. Okay. Firstly, benzene is aromatic. And the characteristics that make benzene aromatic are that it must have an uninterrupted cloud of pi electrons. There can be no sp3 atoms between pi electrons. It must also be cyclic structure and a planar structure, so it has to be flat, sp2 hybridized. And every ring atom must have a p orbital. The pi cloud must have an odd number of pairs of pi electrons. So this is probably one of the most important identifiers. Pi cloud must have an odd number of pairs. So for example, benzene has 3 pairs of pi electrons, and so it is aromatic because it is also cyclic, planar, and every ring atom has a p orbital. So we have 3 definitions for you. The characteristics for aromatic: ring, no sp3 carbons, planar, odd number of electron pairs, and all atoms have delocalized electrons. Anti-aromatic, it has the same characteristics of aromatic except for the number of pairs. So an anti-aromatic molecule is a ring. It has no sp3 carbons in the ring. It's planar. All atoms all atoms could be considered delocalized, and there's an even number of electron pairs. So the big difference between these two, let's highlight odd number of electron pairs for aromatic and even number of electron pairs for anti-aromatic. Now, a non-aromatic molecule is a molecule that is either not a ring, has sp3 carbons, in other words, the electrons are not all conjugated, or is not planar. So non-aromatic is something that meets none of that counteracts at least one of the conditions other than number of pairs. Okay? So those are our 3 definitions. Now we're going to look at some molecules. For examples that are not aromatic or anti-aromatic, so cyclooctatetraene is non-aromatic. It's not planar. It has an even number of pairs. And so because it's not planar, we wouldn't say it's anti-aromatic. We would say it's non-aromatic. Interestingly enough, the term aromatic does refer to having smell, but that's because one of the earlier aromatic molecules looked at was benzaldehyde, which has a sweet smell. Most aromatic molecules do not smell nice, not unless they're esters or aldehydes. So then we have cyclobutadiene, which is planar. So it has no sp3 carbons. It is planar. It is cyclic, but it has an even number of pairs. Even number of electron pairs. So cyclobutadiene is actually labeled anti-aromatic. So cyclobutadiene has an even number of pairs of electrons. That makes it anti-aromatic. And cyclooctatetraene has both an even number of pairs and it is not planar. The fact that it is not planar makes it non-aromatic rather than anti-aromatic. Okay, non-aromatic and aromatic compounds. Cyclopentadiene is not aromatic because it contains an sp3 carbon. So cyclopentadiene has an sp3 carbon. It's non-aromatic and it wouldn't be considered anti-aromatic. It's non-aromatic. Okay. Now, if hydride ion was lost, so to create a cation, this cyclopentadienyl cation has an even number of electron pairs, and so we would call that anti-aromatic. But if we instead lose a proton, and I think this is going to come up in your homework, cyclopentadiene actually has a very acidic proton. And I've drawn it in on the top figure, acidic proton, and I've labeled it, okay? And so this proton has a much lower pKa than normal carbon, sp3 carbon to hydrogen protons. And that is because loss of this proton results in a structure that has 1, 2, 3 electron pairs because it's more favorable for this electron pair to be in a p orbital. This carbon will go to sp2 and then when it goes into sp2 it is planar and with 3 electron pairs, so it is aromatic. So for aromatic molecules, an atom that is normally described as sp3 hybridized, if it will allow it to become aromatic, will adopt an sp2 hybridized orbital and put the electron pair in the empty p orbital. So how do we know that cyclopentadiene's lone pair of electrons are pi electrons? And we know this because of tests showing the delocalization energy and that the lone pair can be used to form a pi bond in the resonance contributor. So in our resonance hybrid, we can see that the lone pair can be moved around the ring so that it forms each of the pi bonds in turn. Therefore, cyclopentadiene is aromatic. Other aromatic compounds, for example, naphthalene, phenanthrene, and chrysene, these molecules have 5 pairs. Naphthalene has 5 pairs of electrons. Phenanthrene has 7 pairs. And chrysene has probably 9. 1, 2, 3, 4, 5, 6, 9 pairs. Notice that all of the atoms are sp2 atoms, and so these are planar structures. And what you should know about these molecules is that they are all carcinogens. And if you want to look up the known carcinogen benzoapyrene and its structure, you will notice that it has a similar structure to naphthalene, phenanthrene, and chrysene, and that it is shown to be a carcinogen. So these molecules are suspected carcinogens or known carcinogens, and they have similar structures. We're going to draw a different type of molecular orbital diagrams for aromatic molecules. What we'll do is draw the ring, and then for each vertice, draw a orbital blank. And so if we have two vertices at the same energy level, then we'll have two blanks to fill electrons at the same energy level. And the same thing for these top two vertices that are at the same level, we get two blanks, and then we have the top energy level. Again, the bottom half of orbitals are going to be the bonding orbitals, and the top half are going to be the anti-bonding orbitals. We fill the electrons from bottom to top. Remember that if you have degenerate orbitals, orbitals of the same energy, we put one electron in one first, the second electron in the other blank, and then fill in electrons as if we still have more. Okay, and the total number of electrons should be equal to the total number of pi electrons, but the total number of molecular orbitals should equal to the total number of p orbitals that are making the molecular orbitals. So since there are 6 p orbitals, one for every carbon, there should be 6 blanks. Okay. For the 5-membered ring, the energy levels are slightly different. Because it's an odd-numbered ring, we have usually more bonding than anti-bonding orbitals. And again, if the vertices are at the same energy level, then we're going to draw those molecular orbitals as being at the same energy level. So I have 1, 2 at the same level, then I'll have 1, 2 molecular orbitals at that level. And the lowest energy molecular orbital will be at the bottom with the highest energy molecular orbital at the top. And you fill the electrons into the lowest energy up to the highest energy.